Hey everyone and welcome. Today we're diving deep into a statistical tool that is, frankly, one of my favorites. It's elegant, it's powerful, and it's incredibly practical. It's called ratio estimation. So if you've ever found yourself needing to make a really good guess about something without having all the information, well, you're going to want to stick around for this. Let's get right into it. Okay, so here's our game plan. We're going to start with the fundamental challenge, why simple estimates sometimes just don't cut it. Then we'll introduce ratio estimation as the perfect solution. From there, we'll explore where you can actually use this in the real world, and then we'll pop the hood and look at the math that makes it all tick. Finally, we'll put it head-to-head with simple random sampling to see when it's better, and we'll wrap up with why this is basically a new superpower for your statistical toolkit. All right, so first things first, let's set the stage. You know, in a perfect world, we'd have all the data we could ever want. But let's be real, we're almost always working with just a piece of the puzzle, a sample. And that creates some really interesting challenges that our standard go-to methods can't always solve. To make this concrete, picture this. You're working for a juice company and a massive truck, just overflowing with apples, backs up to the loading dock. Your boss wants to know, how much juice can we get out of this entire truckload? How would you even start to figure that out? It's a simple, practical question, and it perfectly sets up the problem we're trying to solve. Now, you might think, okay, easy enough. You just take a random sample of apples, figure out their average juice content, and multiply that by the total number of apples in the truck, right? That's our basic estimator. But here's the huge roadblock. Are you really going to count every single apple on that truck to get the total population size N? No way. It's just not going to happen. It's wildly impractical. So our standard approach is dead in the water. We're stuck. And this, right here, is where ratio estimation swoops in to save the day. The core idea is just beautiful in its simplicity. It's all about using an extra piece of information, something you do know, to make a much, much smarter guess about the thing you don't know. So this extra bit of info has a name, of course. We call it an auxiliary variable, which we'll label X. So for our apples, our main interest, our Y variable, is the juice content. What would be a good auxiliary variable, X? Well, how about the weight of each apple? It's super easy to measure, and you can be pretty darn sure it's related to the amount of juice, right? It just makes sense. Heavier apple, more juice. And that relationship, that's everything. Ultimately, what we're trying to figure out is the true population ratio. We'll call it B. As you can see, B is the true average juice content of all the apples on the truck, divided by the true average weight of all the apples on the truck. You can think of this B as the true juice yield per pound for the entire population. But here's the thing. We can't actually know the true B without juicing every single apple. So what do? We estimate it. We take our random sample of apples, we calculate their average juice content, that's Y bar, and we divide it by their average weight, X bar. And that gives us B hat, our best guess for that true population ratio. Okay, so that's the basic idea. But you might be wondering, so what? Why is this such a big deal? Well, let's get into the real-world stuff, because this technique is used absolutely everywhere. I mean, this thing is a statistical Swiss Army knife. Sometimes you just want to estimate a ratio itself, like the percentage of a magazine's pages that are ads. Or, just like with our apples, you can estimate a total when you don't know N, like the number of fish in a giant net, using the total weight of the catch. It's also a go-to method for making your estimates way more precise, for adjusting survey data to match known population numbers, and even for fighting back against non-response bias. It is incredibly versatile. Let me show you a classic example from the U.S. Census of Agriculture. The goal was to estimate the total farm acreage in 1992 from a sample of counties. But here's the kicker. They had the complete data from 1987. Now, just look at this plot of the 1992 data versus the 1987 data. It's an almost perfect straight line going up. That is a super strong positive connection, which makes the 1987 data a perfect auxiliary variable. And this is where the magic happens. Look at the difference it makes. If you just used a simple random sample method, you'd estimate about 917 million acres. But with ratio estimation, we use our knowledge of the total 1987 acreage for all counties. We calculate our B hat from the sample and multiply it by that known 1987 total. And boom, we get an estimate of 951 million acres. It's a much better estimate because it corrected for the fact that our sample, just by random chance, happened to include counties with slightly smaller farms. Okay, so we've seen it in action and it's pretty impressive. But why does it work so well? To really get it, we've got to pop the hood and look at the math. This is where we move from just intuition to statistical proof. All right, here's the big trade-off, and it's super important. Ratio estimators. They're technically biased. What that means is if you average the results from all possible samples, you wouldn't land exactly on the true value. There's a tiny systematic error. However, and this is the key, that small bias is almost always a price worth paying for a massive reduction in variance. Think of it like this. We're giving up a tiny, tiny bit of perfect accuracy to get a huge boost in precision. And most of the time, that is a fantastic deal. And the best part is, this bias isn't some big, scary monster. It gets really, really small, practically vanishes under a few conditions. The most important one is having a large sample size. But the bias also shrinks when the correlation between X and Y is super strong, and when your auxiliary variable X doesn't vary a ton. In most real-world studies, this bias is so small we don't even worry about it. So if we're not too worried about the bias, then the real star of the show has to be the variance. Remember, lower variance means our estimate is more reliable, more likely to be close to the real answer. It's all about precision. So let's put a number on it. Okay, here's the formula for the variance, and don't let it intimidate you. We'll walk right through it. The first part, that finite population correction, you've probably seen that before. The really important part is the second term, S squared E divided by N. The key to everything, the secret sauce to our estimator's precision, is that S squared E term. So what exactly is this S squared E thing? It's just the variance of the residuals. And a residual is simply the difference between what we actually observed for Y and what our ratio predicted for Y. If you picture that farm acreage plot again, the residual is just how far away each dot is vertically from that best fit line. So if your data points are all huddled really close to that line, the residuals are small. Their variance, S squared E, is small, and your final estimate is going to be incredibly precise. All right, this all leads to the big question, the one you're probably asking right now. When do I actually use this thing? So let's settle it. Let's put the ratio estimator in the ring, head-to-head, against a good old simple random sample, and see, mathematically, when it comes out on top. Okay, check this out. We've got the two variance formulas right next to each other. Look how similar they are. The only real difference is what's in the numerator of that second term. For the simple random sample, its precision depends on S squared Y, the total variation in our Y variable. For the ratio estimator, its precision depends on S squared D, which is the variance of the deviations from that true ratio line. So when you look at it like that, the answer is crystal clear. Ratio estimation is better. It's more efficient, it has lower variance, whenever the variance of those deviations around the line is smaller than the total variance of Y. And that just makes perfect sense, right? We win if our helper variable X does a good job of explaining why Y is all over the place. And now for the best part. After you do all the algebra, which we won't do right now, you're welcome, it all boils down to this one beautiful, simple rule. Ratio estimation is going to be more precise than a simple random sample whenever the correlation coefficient R between your Y and X variables is greater than 1/2. That's it. A wonderfully simple, practical guideline you can actually use. All right, we've come a long way, from a truck full of apples all the way to the mathematical proof. Let's bring it all home and recap why ratio estimation is, well, kind of a statistical superpower. So, what's the bottom line? First, it will make your estimates dramatically more precise, as long as you have a correlated helper variable. Second, it lets you work your magic even when you have no idea what the total population size N is. Third, it's a fantastic tool for adjusting your sample so it looks more like the population you're studying. And finally, it can even help you deal with the tricky problem of non-response bias. And that's a wrap on our deep dive into ratio estimation. The question I want to leave you with is this. Now that you have this tool in your back pocket, what hidden data is out there all around you that you could use? What could you estimate about the world with a precision that you never thought possible before? Thanks for joining me.